Welcome to the HiRSE Summer of Testing. This is a collection of tutorials focusing only on testing and is a separate series to the usual HiRSE seminar series.
Hello, my name is Mihaela Jarema, and I am with the academia group at MathWorks located in Munich, Germany, where I work as a customer success engineer. In this role, I get to spend a lot of my time working directly with scientists and engineers at German research centers, so that's probably you. And I make sure that you and your peers make the most of the MathWorks computational tools and services at your disposal for whatever it is that you're trying to achieve. Today, I'll be talking to you about testing with MATLAB in a new episode of HiRSE Summer of Testing. We'll start with the why and the how of writing tests, which will be particularly useful for those of you who are not yet totally convinced that you need testing. For those of you who are already familiar with testing, we'll then dive into more advanced capabilities that are available in MATLAB and the tools that can help you build more robust and sustainable research software. Let's get started with the why and the how of writing tests. I want you to think of your research and the code you write for your research projects. Maybe this already is or will become the next big thing, impacting most other research projects in your area. The prospects are looking good, so new members keep joining your group to extend the capabilities of your code and its applicability. Let's meet one such new member. Met Mihaela. That's me. Assume I've just joined your group to use my experience in some field, let's call it malabology, for your awesome project. For starters, I will contribute with some code almost from scratch, which will later be integrated in the overall code. Let's put ourselves in my shoes. To get started, we'll need to put together the bare minimum of data and code we need from the existing project, which is shown here in an overly simplified version. What we're working with are some items, doesn't matter which, that need to be processed in some manner. Again, doesn't matter which. And initially, we have two types of timestamps that record in the entry timestamps initially the dates and times when our items were received to be processed in whatever way is necessary, and the exit timestamps recording the dates and times when the same items were finished being processed. Now, with this, we'll want to access our data, then go ahead and explore it in some manner to get a better feel for it. Then we'll go ahead and process it in one way or another, and then visualize it to also get some insight into our results and not just do number crunching. Let's go ahead and look at the same code, but this time in MATLAB. Our script consists of 4 sections, one for accessing the data, another for exploring the data, processing it, and visualizing it. And each one of these sections can be run independently of each other and possibly several times, either by clicking on the blue bar here or by clicking the Run Section button. If we run the first section for accessing our data, since our file is a math file, so binary MATLAB file, loading the entry timestamps and the exit timestamps can be done simply by using the load command. And we can see that the two variables appeared in our workspace. Moving on to the next section to explore our data, we can do this in a first instance using whos, and this will list in our command window the variables we've just loaded, including their type and their size. So we can see that they are of dimensions 100 by 1. So 2 column arrays with 100 elements each. And they are of class date time, which is a suitable data type for representing date and time information. If we want to get a bit more insight into either of the two variables, we can also go into the workspace and double-click either of them to open them in the variable editor and have a better look at what these variables contain. With this, we can go on and process our data. For instance, to compute the elapsed durations it took to process these items. And since we're working with datetime information, this is as simple as subtracting the entry timestamps from the exit timestamps. We'll also go ahead and compute the number of durations we have by using the built-in function numL, which returns the number of elements in our durations array. So if we run this section, we'll notice we should have as many durations as we have timestamps, so 100 by 1. And we also use the function min to compute the average duration. Now we also go ahead and visualize the data we have using a simple plot command to plot all our durations. And on top of them, we're going to add a horizontal line with the average duration. So let's go ahead and run this as well. And have also some visual insight into our data. With this, we are now ready to add some functionality. For instance, say we want to add functionality to determine which processing durations took too long. Whatever this too long means, for instance, longer than a specified threshold. Let's go ahead and write a function. As mentioned, we want to add a function to compute which and how many processing durations took longer than a given threshold. So I can call our function, for instance, get long processing durations. For the input arguments, we're going to work with our durations array, as well as a threshold above which the durations are considered as having taken too long. So let's call this duration threshold. For the output arguments, we can have, for instance, the number of durations that have been identified as having taken too long, as well as a logical array. So an array of true or false values that tell whether a duration took too long or not. Let's ignore for the moment the comments and compute our logical array by using logical indexing. For instance, we can get in one go all the durations that took longer than a duration threshold and the number of durations will be computed in a first instance using length of the logical array. Let's save this. Our function is now implemented. Whatever else we might want to do with this function further, at the very least, we want the code to be correct. Or if that's not the case, find out as soon as possible what went wrong and how we could fix it. To this purpose, we can go to the command window and call the function with some input parameters. For instance, we could call it with our durations array and a duration threshold of 0 seconds, which should find all the processing durations as having taken too long. So let's go and call our function with our durations array and a duration threshold of 0 seconds. And let's return just one output parameter, namely the number of durations. Now we can see that this finds all the 100 processing durations as having taken too long, which is what we expected as well. How about if we ran another test and we ran our function with a threshold larger than any of our processing durations so that none of them would be considered as having taken too long? For instance, we can try to repeat the test, and instead of 0 seconds, we can have seconds of 1 plus the maximum of our durations, or it could also take infinite seconds. The number of durations seems to be the same as before, so still 100. Something seems to be wrong. We should have had 0 instead. Now, if we go ahead and we look at the code, it turns out we are using the function length, which returns how many elements there are in the logical array is long, instead of how many of them meet the condition of being larger than the provided duration threshold. Instead of length, we should go ahead and use a more suitable function. For instance, we could use something like n and z, which stands for the number of non-zero elements, so how many true values there are in our logical array. Let's save this and rerun our test. And we can notice that the number of durations is now correctly identified as 0. This seems to have fixed one bug, since the number of durations is now correctly identified as 0. But at the same time, we also want to make sure that this bug fix didn't introduce further bugs. So let's repeat the previous test. And we see that the result is still correct. So far, so good. It seems that our bug fix solved the issue with the second test, and our first test still passes after the bug fix. However, we had to retest things manually. And this could become hard to manage as we carried on adding more functionality and we had to perform more tests. Going shortly out of MATLAB, what if instead of testing manually, we could automate testing our code behaves as intended? Well, we can. Namely, we can use testing frameworks in MATLAB to automate testing our code behaves as it should. In the simplest case, we can use unit tests to test that each unit of our code, for instance, each function, behaves as it should. Namely, that when our code is used in a certain manner, for instance, to compute how many processing durations took longer than 0 seconds, a certain result or behavior should occur. Namely, that all processing durations take longer than that. We can test this in the simplest case using an assert, which will throw an error if the tested condition is false. There are other types of qualifications for testing values and responding to failures besides assertions, including verifications, assumptions, and fatal assertions. For instance, verifications produce and record failures without returning an exception, whereas assumptions ensure that a test environment meets some preconditions. There are also other types of testing besides unit tests. For instance, integration tests to check that your code works appropriately as a whole. But right now, we'll only focus on unit tests. Let's go back to MATLAB and try to convert our previous tests from the command window into tests that can be run automatically. We can easily create a test file with initial test code for our function simply by right-clicking in the editor and then selecting Create Test. This will auto-generate a sample test class with a methods block that has a sample unit test function containing both a call to our function with certain inputs to produce certain outputs and a list a call to verify equal to test this produced output. And verify equal will produce and record a failure if the actual output is not equal to the expected output, but will not throw an exception otherwise. The function must also accept a test case instance as an input. But other than that, we do not need to know any object-oriented programming to fill in this code or add further test functions and parameterization properties using some code insertion options on a tools tree that we'll get to see later on. We can also use other qualification methods than verify equal for testing values and responding to failures, including for other types of qualifications we mentioned earlier, such as assumptions, assertions, or fatal assertions. To complete the test and make it more readable, we can go ahead and rename the class to something else that makes more sense to us. For instance, let's use here an uppercase G, and also rename the function to something else. For instance, we can say test all long. We can then go ahead and specify the inputs to the function under test. If you remember, previously we were loading the timestamps from our binary file, the entry timestamps and the exit timestamps. And we were computing the durations array simply by subtracting the entry timestamps from the exit timestamps. Our duration threshold will be like in our first test, 0 seconds. And then we can go ahead and also mention the expected outputs when calling the function with its inputs. Namely, the expected number of durations will be as long as there are elements in our array of durations. We won't be needing the second output, so let's remove that. And then we will also not need the second verify equal. And then we can also go ahead and use here an operator to ignore the second output. There's no point wasting time and memory with what we do not need. Let's go ahead and save our test as well. And we're good to go with having transformed our first test. Fast forwarding a little, we added several other test functions, striving to test everything we can anticipate that could go wrong. Since we're aiming for good coverage, good candidates are, for instance, testing how a unit should behave for edge cases. That means besides the beginning of a range, like in our first test, we can also look at the end of a range, like in our second test, and at least at another point, another internal point, such as the median, because this will help us get a good coverage over the range of values. We can add our test functions either programmatically or also interactively from the tool strip here. We can go ahead and insert an appropriate method at the desired level. And later on, we'll also be using this to insert parameterization properties. Once we are done with writing our tests, we can go ahead and run them either interactively from the button here using either the default version or potentially customizing our test run as we see fit. We can also use the test browser app to run our tests. We find this here among the apps, and we'll have a look at the test browser app in a couple of moments. Or potentially, we could also run our tests programmatically. For example, using the run tests function. But let's go back for the time being to our editor and run our tests interactively. As soon as we'll click this button, this will also bring up the test browser app and run all the tests in this file here. And we can initially see that all our 3 tests passed and none of them failed. And we have a couple of other options we can look at. For instance, we can rerun our test file, remove one or several of the tests, We could also go ahead and add additional tests, or we could also enable a parallel test execution if we have plenty of tests and we want to make them run faster. We can also use the test browser app to interactively collect code coverage for all the tests we are interested in. To this purpose, in the app, we open the coverage settings, then enable coverage reporting, and choose our desired metric here. For instance, we can stick initially to statement. Then we're going to go and add the source files we're interested in our case, the function we were testing, and then rerun our current suite of tests. As the tests run, code coverage information is collected in a report to detail which parts of the source code were executed by the tests. In our case, the code coverage reports contains coverage results for our chosen coverage metrics. So we're looking at whether every statement in our source code was executed at least once, or whether every function in our source code was called at least once. There are also other types of coverage, as we got to see. For instance, we have decision coverage, which looks at branching and control flow statements, or also condition coverage, which determines whether every condition in our source code has been evaluated to both true and false. The report also contains or uses different colors to highlight the statements that got executed or statements that may have gotten missed in case we failed to achieve 100% coverage. So then we can go ahead and create further tests to execute any parts of the source code which we may have missed. If we now go and look again at our tests, one thing we'll notice is that every test has pretty much identical code for loading the entry and the exit timestamps and computing the elapsed durations it took to process the items. This is not particularly efficient. It can also make our tests slower. One way we can avoid duplicated code to load these timestamps and save time to compute durations only once is by extracting this setup code into something called test fixtures. Test fixtures are setup and teardown code that sets up the pretest state and then returns it to the original state after running the tests. And we can add them programmatically or interactively from insert method. We can insert test fixtures either at the method level, where the setup and teardown code would run before and after each test, or we could also do it at the class level, where the setup and the teardown code runs before and after all tests in the test class. And this is what we want to have here. So let's go ahead and add a method at the class level. In this fixture at the class level, we want to load the entry and the exit timestamps only once for all the tests, and compute the elapsed durations it took to process the items only once for all tests. So let's go ahead and first rename the function to something that we find more appropriate. For instance, we can call the function durations setup and go ahead and load the entry and the exit timestamps from our data set. And now we can go ahead and compute the durations as before by subtracting the entry timestamps from the exit timestamps. Unlike previously, we do not want to have durations as a local variable to the function, but we want to use this here as a parameter across all tests. So to this purpose, we want to add durations as a property of the test case instance, which we can do programmatically or interactively from insert parameters. For instance, let's choose class setup parameter. Now, this here looks a bit more complicated, but we don't have to make it as complicated as this. So let's just remove everything else except the parameter we're interested in. And as mentioned, it is this parameter that we want to use instead of the local variable. So let's use the code analyzer to help us correct this here. And before going ahead and correcting the use of durations in all the other tests, let's also add some teardown code, which will run after all the tests in the class run. And in our case, what we could possibly do is, for instance, use the function clear to clear some variables, such as the exit and the entry timestamps. To call the function clear, we'll use here a function handle to the function we're interested in, and then mention the two variables we want to clear. With this, we are good to go here. What we have to do is go through all of the previous tests and correct them so that we no longer have this duplicated code. So we no longer need this line of code here. We also do not need to compute the elapsed durations anymore. And instead, we will be using the parameter of the class, so the property of the test case instance. And you can use that faster. We can correct this faster using the code analyzer. For instance, either by clicking here on fix or by right-clicking, or we could also do this directly from this part and fix it from here. Of course, we shouldn't forget to no longer load our data set and compute things. I think I have corrected pretty much everything. Let's actually increase here the width and no longer open the coverage report run and rerun all the tests to make sure we haven't introduced any bugs while modifying our tests. It seems we're good to go. All tests pass. Being able to check our code behaves as intended, quickly and verifiably, like we have just done, can be very helpful because our code will carry on changing with new requirements, either as we go ahead and add new features, change behavior, improve design, or whatnot. Let's look at an example. Say we would like to modify the function getLongProcessingDurations so that we are able to call it with just one input parameter, durations, and with no duration threshold input. So the function itself should be able to use a suitable value for the argument instead. To this purpose, we can go ahead and modify the function. However, at the same time, we want to make sure we do not break any existing functionality in doing so. So instead of modifying the function here, let's go to our test file and add another test, a test That should pass if we can call our function getLongProcessingDurations without a duration threshold input parameter. And we can do this without getting an error. So the test passes successfully, for instance, if no exception is thrown while running the function with just one argument. So let's go ahead and add another test, which we can call, for instance, test no duration threshold argument. Our input will be as before the test case. And what we want to do here is to be able to call our function getLongProcessingDuration with just the first input parameter. So just the durations. And as we do this, we should not get any exception. So for instance, if we put this in a try-catch block, we should have an empty actual exception. Let's also indent this nicely. And verify that the exception stays empty. This new test that we have just added should fail because we have yet to write any code to change the behavior of our function accordingly. So if we go here and rerun all our tests, we do indeed notice that the test fails. On line 65, the verify empty failed because we called our function with not enough input arguments. What we've just done is also known as test-driven development, where before writing any code to implement some behavior, we first write the test to verify our code behaves as expected. And this test will initially fail. To make the failed test pass, we could, for instance, go and modify our function, for example, by checking for the number of input arguments, and if this were 1, so we'd call our function without the duration threshold argument, then we could set the duration threshold to some value, such as 3 times the standard deviation of the durations argument. This is fine, but it is also suboptimal because we end up adding code in the body of the function to make sure we run the function code only on valid inputs. And this can make our code harder to read and maintain, as we might have to increase the number of checks on our argument. A better way instead is to use something called function argument validation, which we can use to declare specific restrictions on our input arguments. Such an arguments block will come before the first executable line of our function and is the way to constrain our arguments in terms of size by specifying the dimensions that the argument should have, if any, where a column for a dimension indicates that any length is allowed in that dimension. We can also restrict in terms of class if our input has to be of a certain type, and also in terms of other aspects by using validator functions. These validator functions can be either MATLAB functions or custom functions we wrote ourselves. We can even add a default value for optional input arguments like our duration threshold. And with this arguments block, we can restrict our input arguments without writing any code in the body of the function to perform these tests. Now back in MATLAB, let's have a look at how we can modify our function getLongProcessingDurations to use an arguments block and restrict our input arguments. So before the first executable line of code, we'll go ahead and add the block. Then we'll take each argument in turn in the order in which they appear here. So we'll start with durations, which you know is an array of dimensions any by 1 and of class duration. Our duration threshold is a scalar, so dimensions 1 by 1, also of class duration, and we do want to make it an optional argument. So let's add a default value that can be used if the function is called with just one input argument. We can, for instance, use 3 times the standard deviation. Let's save this, go back to our tests and see if everything now passes. All tests pass now, so we're good to go. Now, quite confident that the added functionality does what it should, the new colleague is eager to integrate her code changes in the shared code base. Let's have a look at how this would work. To make sure the code is easier to develop collaboratively within the project, as well as to streamline workflows and improve code quality, the team has already taken a number of steps. For instance, they use source control, in this case GitHub, to make collaboration easier and keep track of the code changes. They also use something called MATLAB projects to automatically set up the working environment for everybody working on the project and make the code easier to maintain and extend. And also, since tests are only as good as you get to run them, they also use continuous integration, in this case, to automate the building and testing process and help identify issues early. Here we see our remote Git repository on GitHub, so the place where the code for the entire project is stored. The repository also contains a GitHub workflows directory where we store our YAML files to define our workflows. A workflow is a configurable automated process that will run one or more jobs on a runner machine when triggered by an event in our repository. For instance, we can have an automatic checkout and test triggered by a push request. Workflow files use YAML syntax. This is directly readable and writable by humans. So let's have a look at our workflow here. The name of the workflow is generate test artifacts. And under on, we see that a push will automatically trigger this workflow and cause it to run. A workflow also consists of one or more jobs. In our case, we only have one job. And each such job has one or more steps that either run a script to define or run an action, where an action is a custom application that performs a complex but frequently repeated task. So basically, we can use an action to help reduce the amount of repetitive code that we write in our workflow files. In our case, on a self-hosted runner machine, we first check out the repository to the runner. To also run MATLAB in the workflow easily, we can use specific MATLAB actions from the GitHub MATLAB Actions repository that I'm showing here. In our case, we use the run test action to run the test in our project, and we also use some optional inputs to generate test results in JUnit style XML format and code coverage results in Cobertura XML format. Note that since our repository is public and without transformation products, and we're also using a self-hosted runner machine, we can do all this without having to worry about setting up a license. Coming back to the files on our own computer, in MATLAB, we first go ahead and open our MATLAB project by double-clicking the file with the PRG extension. A MATLAB project is a scalable environment where we can manage MATLAB files, datasets, tests, and whatever else we need in one place. Compared to previously, our datasets and our tests are each extracted in their own folders, but everything should be the same otherwise. Also, for the run MATLAB test action in our GitHub workflow, all our tests have a test label. The MATLAB project also allows us to work with files under source control and perform source control operations such as committing code, merging changes, or viewing revision history. Or you can also use the MATLAB Git API. If you prefer writing commands yourself, you can also go ahead and enter commands directly in the MATLAB command window by prefixing them with the exclamation point operator. So the command will be performed directly by the operating system. Let's do this by first using git status to display the state of the working directory and of the staging area. And then we can go ahead and commit our newest work with an appropriate message and then push to try to upload the local content to the remote repository, which should trigger our workflow to generate test artifacts. So let's go ahead and commit using an appropriate message. Let's check our status again and push. Coming back to our remote repository and our workflow, we can go ahead and look at the runs. And let's check specifically the run tests action. Let's look primarily at the run command. Now, using the run MATLAB tests action in our workflow automatically runs tests authored using the MATLAB unit testing framework. And by default, this includes any files in our project that have a test label. And if we look here, we'll recognize all the 4 tests we had looked at earlier, and we are happy to see that they all pass. So we're good to go. We've come to the end of our video on testing with MATLAB. Thank you for joining me on this journey. We've covered a lot, but there's always more to explore. For additional resources and insights on everything we've discussed, and even more topics we can get to, visit this curated resource page, for which you can find the link in the description of the video. Happy testing!
Thank you for watching this tutorial. Please check out the slides on Zenodo linked below and see you next time.